Okay, now I'm ready.
I'm so glad. All right. So here's the confusing part. In your book, this is section 4.1. In the Larson book, whose homework we're taking, it's chapter 12. And in our chapter, we're kind of considering this whole thing to be chapter 14, so I'm consistent with the rest of it. So it's a one-off section from a different part of your book that's using a different part of another book to call the middle of chapter 14. But this is very much about limits. And what this mostly has to do with this concept that we call end behavior. And because we can, we're going to spell it in the British way, because that's fun. Yes. You have seen some abbreves with this. Do you remember what this abbrev meant? Abbreviation.
What does your handwriting say up there?
Larson, 12. Our. We'll say this chapter, 14. You're recording this for all time. I'm just going to laugh as like 10 years from now I remember this. So, oh yeah, this will be great.
Whenever I come back here, I'm going to make sure I see you if I can look.
Your kids will hear this.
Oh no.
Of course, that's a frightening prospect as it is.
What if my sister comes here?
What does HA possibly stand for? It does.
I would be like 25, 26. Still a great time. Gosh, she might get bullied though.
Okay. So a horizontal asymptote is a specific kind of asymptote. It's very, 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 very specific to where you have a horizontal line. So where I kind of need you guys to step back with end behavior is what you're doing is you're zooming out sufficiently far on a graph. You're zooming out so far that you're looking at what the, I'm going to put in quotes, real character of the graph is. The character that happens when you don't consider things like divide by zero, where all the crap that happens in the middle of the graph doesn't matter. So horizontal asymptotes are one kind. We also have something called an EBA, which is another abbreviation used. This abbreviation means End Behavior Asymptote. Similar idea, but it's much more general. We've also used OA before, which means Other Asymptote. And so I want you guys to know, like really what I'm trying to do is take a lot of these concepts and throw them all at the same thing. So the idea of the limit at infinity, the HA, the EBA, the OA, this is all now one. It's all one pop thing. Get back. There are, but that's not an end behavior. That's a middle behavior. Vertical asymptotes are specific to a location, a locus. End behavior is not specific to one location. It's furthering out on either direction. Okay. A couple of basic facts about end behavior asymptotes. This is probably the most common limit that we have. I dissect this because when we talk about limits to infinity, we really mean this. This is a notation that we can use, and I'm going to fix this here. Limit as x approaches infinity. You can approach infinity and you can approach negative infinity. The limit as x approaches infinity of 1 over x would be what? What happens as the graph gets really big? Miguel?
It gets really
what? 0. It gets really, really, really tiny and approaches 0. Contrast that with this, the limit as x approaches 0 from the right side of 1 over x. So this graph looks like this. And so as I approach 0 from the right, what does the graph do? Yeah, it goes to infinity. So given that, this is supposed to be an infinity symbol. Sorry, I closed Chrome and yet it's still freaking out on me, just saying.
Because you have the actual Chrome window still open.
I do? I do. Oh, son of a...
Good catch, Connor.
I have multiple ones open. If that fixes a certain problem, then I'll be very happy, but we'll see if it fixes the one that I'm referring to. Okay, next. The limit as x approaches infinity of 1 over x squared. What would that be? Tell me what you instinctually think.
0.
0. It does. Doesn't necessarily matter how quick. What I want you to kind of break this down into is that this is the limit as x approaches infinity of 1 over x times 1 over x. You don't have to expressly write that, but that's why you can prove it's infinity based off a previous piece that we did. So now I'm going to give you the limit from what we call, technically this is referred to as a p-series, or it can generate a p-series, but the limit as x approaches infinity of x to the p, this is going to be equal to 0, but only for what p-values? Greater than 0. What would this be? The limit as x approaches negative infinity of 1 over x. You go. Yeah. We'll just say 0. It is 0 from the negative side, but it's going to be 0. We don't really distinguish it too far. So I want to take all of this, and now apply it to a problem. Ready for this? Every piece I just did should now be able to get us like 90% of the limits that we're going to face as we approach infinity. The limit as x approaches negative infinity of x to the 6th minus 2x to the 5th plus 4x to the 4th over x to the 7th plus 1. Okay. I know at some point you guys may have talked about what happens when the degree of the numerator is less than the degree of the denominator. But I want to do a very different strategy here. What I'm going to do with this is I'm going to multiply the numerator and the denominator by 1 over x to the 7th. And I'm going to do this because that's going to completely change all of the terms to become ones that we can use this idea of what happens when I go 1 over x to a power. So we still have the limit as x approaches negative infinity. But I'm going to change x to the 6th times 1 over x to the 7th is 1 over x minus, this becomes 2 over x squared plus 4 over x cubed over 1 plus 1 over x to the 7th. Now, which of those pieces now has a limit as x approaches negative infinity that gets you to 0? Which ones? Carlos, what? Well, the 1 doesn't approach 0, but... Say that louder. AirPods.
The 1 is the limit when x approaches infinity.
Why?
Because the 1 over x to the 7th becomes exponentially small. So it's small when you get to higher and higher.
So that becomes 1 plus 0, right? What about these three pieces here? What do they become as x gets really, really, really tiny or big? They all become 0, right? You're going to get 1 over a stupid large number, whether it's positive or negative. You get 0 minus 0 plus 0. What is 0 minus 0 plus 0 over 1 plus 0? 0. The entire limit is 0. And look back at the original problem. This should actually make perfect sense to you. As you plug in a super large or a super small value of x, the part of this fraction that overpowers the rest of it is the one with the largest power. The x to the 7th becomes so much more powerful than the x to the 6th, the x to the 5th, or the x to the 4th. It overshadows it. And if it doesn't happen early on, it will happen later on. Much, much, much later, but it will. And so essentially what's happening is that the denominator is overpowering the numerator. Eventually, as you get to infinity, it will. The denominator will become so much larger than the numerator. And when that happens and you go to infinity, you basically hit 0. So underneath, I want you to write the degree of the denominator was greater than the degree of the numerator. the degree of the denominator was greater than the degree of the numerator. And this rule is that the limit as x approaches infinity of x to the p over x to the n is equal to 0 whenever what is true? Chris, what? When n is greater than p. When the degree of the denominator, and this is true of any polynomial that could happen in there. It could be any sum or difference of that. And the proof was one we just did. So that's the case where the degree of the denominator is greater than the degree of the numerator. Ready to flip that around? Okay. We're now going to look at what happens when the degree of the numerator is greater than the degree of the denominator. So we basically said anytime the degree of the denominator is greater than the degree of the numerator, the limit as x approaches infinity or negative infinity is going to be 0. When the degree of the numerator is greater than the degree of the denominator, okay, we need to actually evaluate this now. Limit as x approaches, as x approaches infinity of x squared over x plus 1.
So could we write for the one above that we just proved, could we do plus or minus infinity on the right-hand side?
Where? What do you mean plus or minus infinity?
Like stuff in purple.
Oh, you could. Yes. I see what you're saying there. Okay, what's going to happen here? One over what? Let's try that. I'm gonna kind of go to the process, and then we'll get to the result here of what's happening. But this is a proof process. We can multiply by 1 over x squared and 1 over x squared. And I like to think about this as removing all unnecessary pieces and only looking at the necessary parts that remain. 1 over x plus 1 over x squared. And as you plug in infinitely far x's, which pieces go to 0? And you get 1 over 0 plus 0, which is what? Undefined, or when we talk about undefined in this case, that's infinity, really. It's an undefined infinity. It's 1 over 0, but it's not really 1 over 0. It's 1 over as it's approaching 0. This basically means that x squared over x plus 1 blows up as x approaches infinity. That's not a very mathematical, technical term, but it blows up because the numerator is going to get bigger faster than the denominator. So as x gets really, really, really large, the entire value of the thing also gets really, really large, and it doesn't approach anything. The word for this, there is a word that I should introduce now because we're not going to really talk about it much until a year from now, this is divergent. It blows up in a way that doesn't converge to anything. It diverges. Now, another way to analyze, and I want you to know this way because this also plays into stuff that you have, is if it doesn't diverge to any specific number, it's divergent. It doesn't mean that it doesn't have character. And we want to at least figure out what the character of this is. Jock, with me? Okay. That should say another way to analyze, so let's slide that over. It's hard to talk right and record at the same time. Another way to analyze. What I want to do with this is I want to take x squared and divide it by x plus 1. I want to rewrite this in a different way. Now, there are 3 ways to do this division. One of them is synthetic division with -1. The other is long division. Of course, I'm going to use neither, and I'm going to use my division. My division is to say, what is the one term I would need to add to x squared to make it divisible by x squared plus 1? That wouldn't make it divisible by x plus 1. It has to be a plus an x, because then you'd factor the x out. Now, because I added the x, I will also now subtract an x to maintain that equality. X squared plus x is now divisible by x plus 1, but the negative x needs something else to be divisible by x plus 1. -1. Because I added the -1, I must now add what to compensate? +1. And then when I divide this all out, using the distributive property, the first division step becomes an x, the second division step becomes a -1, and the final piece becomes 1 over x plus 1. It's a little clean. You can use any other way to divide it as well. What this means is that this is now the function, but it's essentially like we're keeping pieces, so that sort of, I'm putting a little sort of because this isn't really how it is, it's sort of like the limit as x approaches infinity of x minus 1 plus 1 over x plus 1 is the same as the limit as x approaches infinity of x minus 1. Because this piece here goes to 0. So what you get is that the graph it looks like x minus 1. For large or small x values. When I say small, it's tricky to talk about small because small here means like infinitely far negative as well as infinitely far positive. But that's really what's happening. This graph is basically the same character as x minus 1. So we're going to switch over and actually kind of show this, which means, yes, Connor, I have to open up Chrome. I know. So let's get this going with a Desmos thing. Here, let's see. Sorry, Drock, I started to write D's. Instead of Desmos, I put D's. Shouldn't write that. It might mean something different.
It's not a school appropriate term.
I don't know what you're referring to.
I don't know either. But I think we're on the same page.
Are we? Okay, we got this. And then I'm going to graph y equals x minus 1. And I think when you guys see that I zoom out sufficiently far, they are essentially the same graph. Y equals x minus 1 and y equals x squared over x plus 1 become the same graph because that x minus 1 asymptote is just so far in there. Like, you can't see it because we're 100,000 units to the right and left. As I zoom in, the distortion caused by the divide by x plus 1 begins to manifest. And as you get closer to x minus 1, the graph now gets distorted. And that's the distortion caused by the vertical asymptote at x equals -1. So that's sort of what you need to kind of understand about rational functions like this, is that it's sort of like there's a localized distortion happening at x equals -1, but when you're not at x equals -1, you might as well just be on the graph of y equals x minus 1. Because you are so very close that you could be said to be the same thing. And when I say very close, and I'm moving out to this, I'm talking about within a closeness of a scale that just doesn't matter in terms of how close it is. Decimal places that if you're not going to be that far out, well, okay, so if you're 10 to the 10th out, and you're 10 to the 10th close to something, just recognize how freaking close that value is. And you can always just keep going, zooming out until it's crazy, crazy close. So back to the point of this. Let's kind of summarize this with a little bit of some math lingo. The limit as x approaches we'll say infinity. X approaches infinity of x to the p over x to the n is equal to plus or minus infinity whenever p is greater than n. It's going to be up to you to determine if that is a positive or negative infinity, but you can do that just by checking values and seeing whether it's getting far positive or negative. For instance, if I had something like this, limit as x approaches infinity of negative x to the 7th over x, I think you guys would agree with me that that's going to be a negative. Or let's just do an x plus 1 so it doesn't divide. I think you can agree that that would be equal to negative infinity because as x gets really, really large, the value gets really, really, really negative. But you can tell that by looking at these things. Okay, next, let's go to number 7. Ooh, let's create a little break here. Keep my my headings consistent. This is going to be when the degree of the numerator is equal to the degree of the denominator. So we'll do an example of the limit as x approaches infinity of 7 plus x minus x squared over 3 plus 2x squared plus 7x. Does anyone want to give me a hypothesis on what this limit is actually going to do? As x gets really large, what do you think this entire fraction is going to approach?
1.
It's a good guess. Won't be 1. Close.
1 half.
Closer.
Negative 1 half.
Yes. Why?
Well, the 2 squared, the x to the 2, yeah.
That
Yeah, and then
and that. Nothing else matters. The only thing that mattered was the largest power in both of them, and they are the same power. What's essentially happening is this is acting like negative x squared over 2x squared. And since it's acting like negative x squared over 2x squared, it's really acting like negative 1/2, because everything else is basically going to cancel. Now, let's prove it using the tactic we did before. We're going to multiply the numerator and denominator by 1 over x squared, which is going to show you how we can wipe out anything that doesn't matter using these limits. Limit as x approaches infinity of 7 over x squared plus 1 over x minus 1 over 3 over x squared plus 2 over x plus 7. And when I plug that limit in, I get lots of zeros. It was, where what? Oh, it should be plus 2 and then plus 7x. Thank you. I didn't have it in descending order because I was trying to be tricky and I tricked myself. Okay, the ones that don't matter are the 7 over x squared and the 1 over x's. Those become zeros. And this becomes my limit. And that's a little proof of why that is negative 1/2. You guys should be able to look at this and tell right away. The limit as x approaches infinity of x plus 1 over x minus 2, what would that be?
1.
Yeah. We look at the degree, the greatest one there, the leading coefficients when put in descending order. And this is the rule that we kind of have, and I want to summarize this in general. Like, let's kind of put a little summary. Little a. Let's write this in math speak. So we'll do limit as x approaches infinity of x to the p over x to the n. And we'll put a little a. When p is greater than n, we're going to divide and find an end behavior asymptote, because the limit is plus or minus infinity. When p equals n, we're going to look at the ratio of the leading coefficients. And when p is less than n, the limit is what? When the degree of the numerator is less than the degree of the denominator, what's your limit? When the denominator blows up so much faster than the numerator. Carlos? 0. Okay. Your homework is in the Larson section, and we'll see if that's been copied or not, but if it's not, we'll throw it up for a little bit. And let me stop this.